everybody, in this video we're going to look at the two laws that come into play when we're talking about currents, magnetic fields, and charges. Both of these laws involve a version of the right-hand rule. The first one I actually introduced in last DL summary. It's called the Biot-Savart law. The Biot-Savart law tells us what a magnetic field looks like around a current. Suppose we have a current that's traveling straight up. What will the magnetic field look like around this current? To do this, we use the right-hand rule. We take our thumb and point it in the direction of current, and then our fingers curl in the direction of the magnetic field. Notice on the left-hand side of this wire, our fingers are curling out of the board. On the right-hand side of the wire, our fingers curl into the board. So the magnetic field around this wire looks like this. Remember that circles with dots represent things that are coming out of the board, and circles with X's represent things that are going into the board. So the magnetic field is curling like this. Magnetic fields always point around currents like this. But how strong is this magnetic field? You actually have to do some calculus in order to solve this exactly. But we're just going to give you the result. The strength of the magnetic field around a current is given by this equation. Mu naught is known as the permeability of free space. It's just a constant. You don't need to memorize it. I is the magnitude of the current that is flowing, and R is the distance away from the current. As we expect, the farther we get from the source of current, the weaker the magnetic field. Now let's look at the other law. It's known as the Lorentz force law. The Lorentz force law tells us what force a charged particle will feel if it is traveling through a magnetic field. Let's suppose we have this setup. We have a magnetic field that is pointing out of the board in this region. We don't care about how that magnetic field got there, we just know that it's there. We're going to send this positively charged particle through the magnetic field, and we want to know what direction the force will be on the particle. To do this, we need to use a slightly different version of the right-hand rule. In order to calculate the direction of the force, we take our right hand and point it in the direction that the charge is traveling, and we then have to curl our fingers in the direction that the magnetic field is pointing. When we do that, our thumb will point in the direction of the force. So let's try that here. We point our fingers in the direction that the charge is traveling, and then curl them in the direction that the magnetic field is pointing, in this case out of the board, and our thumb points in the direction that the force is. So the force on this charged particle will be downwards. What would happen if we flipped this magnetic field around so that it was pointing into the board instead of out? Well, let's just do the same process. We point our fingers in the direction that the charge is traveling, curl them in the direction that the magnetic field is pointing, and then our thumb points in the direction of force. In this case, it's up. One of the interesting implications of the Lorentz force law is that particles that are moving in the same direction as the magnetic field feel no force. Consider the same setup, except now the magnetic field is pointing in the same direction that the charge is traveling. Let's try to use the right-hand rule and see what happens. We point our fingers in the direction that the charge is traveling, but how do we curl our fingers in the direction that they're already pointing? The answer is we can't. We can't actually apply the right-hand rule here. And it turns out that the force on this charge will be 0. Let's apply these rules to one of the examples that we did with the cathode ray tube. First things first, let's use our right-hand rule to figure out the direction that the magnetic field from this wire points in the area that we're interested in. We don't actually care what the magnetic field is over here. because we're interested in understanding the behavior of the electrons in the cathode ray tube. So let's use our first right-hand rule. We point our thumb in the direction of the current, and then our fingers curl in the direction of the magnetic field. So over by the cathode ray tube, we expect the magnetic field to point this way, out of the board. What force will this cause on those electrons? Well, the electrons are moving from left to right. So let's just apply the second right-hand rule and see what it tells us. We point our fingers in the direction that the charge is moving, and then curl our fingers in the direction of the magnetic field. So the force should be down, right? Actually, not quite. If you look back, you'll find that when we did this example, the force on the charge was up. But why? Well, the reason is that the charges here are negative. They're electrons, so they have a negative charge. With electrons, we have to flip the answer that we get from the right-hand rule. Well, the right-hand rule would usually tell us that the force on these charges was down. The fact that they're electrons and therefore negatively charged means that the force will be up. But what will the strength of this force be? As before, we're not going to be concerned with where this comes from, but we have a formula that tells us how strong the magnetic force on a moving electric charge is. This equation says that the strength of a magnetic force on a moving charge is equal to the value of the charge times its speed times the strength of the magnetic field multiplied by the sine of the angle in between the velocity of the charge and the magnetic field itself. We see here why the force on a charge that's moving in the same direction as the magnetic field is 0. If the magnetic field and the charge are pointed in the same direction, then the angle between them is just 0. And the sine of 0 is also 0. So we get that the force is equal to 0. Now you might have thought we were done with electricity, but it turns out we're not quite yet. Remember how I said that electricity and magnetism are actually very closely related? Hopefully from this example, it's obvious that this is the case. After all, we have a current here, and it's producing a magnetic field. But it turns out that there's even more interesting ways that these two phenomena are related, and we'll start to see that next DL.